Thank you. So I'm going to talk about a coupled atom cavity system and how it can be used as a sensor. So I will jump straight into the topic. So we work on cooling and trapping of atoms and ions. And so in this context, how is a typical measurement done? So if if there are species which interact with light, in that case, you can look at the fluorescence or the absorption. So if you have atoms, for example, let's create a BEC, and you go through all this trouble of changing the powers of different beams and changing the detunings and magnetic fields, and at the end of 5 or 10 seconds, you have a BEC. And then how do you know you have a BEC? You take an absorption imaging, so and in the process, you destroy your BEC. And then if you want to know something, whether some process is happening, you change something and repeat the procedure. So it takes long, and it's a destructive measurement. So what about ions? So there are classes of ions, which are these calcium, barium, which are optically active. So you can look at their fluorescence. They form crystals. So this is an example of a calcium crystal, which you can look on an image on a CCD. And what this image is showing is that it is reacting with some rubidium atoms which are present there. And so the calciums are vanishing slowly. The problem is this is a non-destructive detection for the ions, but this light itself is changing the interaction between the atoms and the ions, and also the state of the calcium ion is getting changed because of the presence of a light. So, but then there are other species which are these kind of ions, which are the ions of alkali metals, and they actually do not interact with light. By which I mean they do not have any transition in the visual or infrared, ultraviolet rays. So these are the kinds which we work on in our lab. So I'm just showing an example of what kind of experiments we do. So in this, what I'm showing is we want to study the interaction between ions and atoms. So we trap atoms, and then we create some ions, and then we hold these ions in presence of the atoms or in absence of the atoms, and see if there is any collisions or something else is happening. So that's this curve. And so how do we know if something is happening to the ions? We basically, at the end of the whole time, we detect the ions by throwing them onto a charge-sensitive detector, and then we count how many ions are left. And in the process, we destroy all our ions. So that's good, but then this process is destructive for the ions, and it takes a while because you have to repeat this. This is a long sequence. So it would be nice if we can come up with a non-destructive way to measure these ions. So which brings me to our experimental setup. So basically what we have is we have a pair of mirrors which forms a Fabry-Perot cavity with low finesse about 650, so line with about 5 megahertz. And if you want to probe this cavity, we send a light from one direction and look at it on a PMT. And then within this cavity, we trap atoms shown here in this red sphere. And these atoms are trapped in a dark mott. If you don't know what it is, it basically all the atoms are in the lowest ground state, F equal to 2 state in this case, so that there is very little fluorescence in this system, so that you can do a detection which is background free. And then if you want to create ions, we shine a blue laser beam which ionizes some of the atoms and creates ions. And if you have to trap those ions, then we apply some RF and DC voltages on these electrodes, which are these wires shown here, and we trap ions. Now the question is, how do we know if there are trapped ions without destroying them? So for that we use this coupling between these atoms and the cavity. So let's see how we do that. So here's the energy level diagram of rubidium 85. So atoms are basically all in this state, but for the moment just consider that there are no atoms in the cavity, but you tune the cavity length such that it is resonant with this F equal to 2 to 3 transition frequency. So in this case, if you take a probe laser and scan its frequency through the cavity, then you basically get a Lorentzian transmission peak, just a Fabry-Perot peak at the frequency omega 2, 3. And this gamma and kappa are basically the loss rates from the cavity and the atomic anxiety state. Now, if you put a single atom in this state, what happens is this atom is also essentially an oscillator, and then it is tuned to the cavity, which is also another oscillator. So these two are coupled, and it turns out if you put a single atom, the coupling is rather small, 0.1 megahertz, which is much smaller than these decay rates, so it doesn't couple strongly. But then if you put lots of atoms, this coupling goes up as square root of n. So if you have more than 10 to the power 4 atoms, then you will get, okay, you will have GC, which is much greater than these loss rates, and you will enter the strong coupling regime. And in this case, if you repeat this procedure, to scan your probe laser frequency, you will have 2 transmission peaks, and the separation between these 2 peaks is basically twice this GC. So if you can measure this separation, then we will know how many atoms we have in the cavity wall. So now, if what happens if we trap ions simultaneously, these ions are at a much hotter temperature, so they're flying very fast. So basically, they essentially knock out these atoms from the atom trap, which means they should reduce the number of atoms, which means they should reduce this splitting, and that should give us show us that there is some ions present. The question is, can we detect this? And it turns out we can. So what I'm showing you here is the experimental result. The top curve is the case when we have only atoms, and then when we shine on the blue laser, but the ions are not yet trapped. So some ions are created, so the atoms are lost. So there is a reduction in this splitting. And then we turn on our ion trap, and so now the ions are trapped, and they collide with the atoms, and they knock the atoms out. So there is a further reduction. So of course, if you increase your laser power, the number of ions increase. So there is a further reduction of this splitting. So clearly we can detect it, but can we do more? Can we say how many of these we have, how many of these ions we have? And it turns out we can. So for that, we have to look at this a little bit at how the MOT or the atom trap loads. So let's say at t equal to 0, you start on all your lasers to load the atoms. So this is what let's see you're recording a fluorescence. So this is how it will look. It will go up, the fluorescence will go up, and this is basically can be modeled by this equation. So what this equation is saying is that the rate at which the atoms are loading is equal to some loading rate, which depends on how much background atoms you have, and then all the other terms are basically losses. So this term gamma BNA is the loss due to collisions with arbitrary gas in the vacuum chamber that knocks the atoms out of the atom trap. This gamma PNA is the loss due to the blue laser. Then this term is the loss due to collision between atoms themselves in the MOT, but this is small in our experiment, we can neglect this. And this last term is the collision between atoms and ions, which is also knocking out atoms from the ion trap. So now let's say first you only have atoms and there is no laser, nothing else. So all these terms except these 2 can be dropped, and then we solve this equation. You basically get this kind of exponential rise to saturation, and the saturation atom number is here given by Na infinity, which is about 10 to the power 6. So we can measure these numbers and the loading rates and gamma B, and a fraction of these total number of atoms are actually coupled to the cavity, and we determine that to be about 8%. And then now if you probe the system using our VRS technique by shining the light and looking at the frequency splitting, we get about 60.4 megahertz, which was the topmost curve in the previous slide. Now if you turn on the blue light, this term comes into play, but this looks exactly like this, similar to the other term, so it's easy to write down the solution. And then we do some algebra. What we measure is the new splitting, which is a slightly reduced splitting, which we measure, and then we can recast this using all these equations. We can find what gamma P is, which essentially depends on the measured values of the splittings, and gamma B, which we also have measured. So we can determine what the photoionization rate is. Now what happens if we turn on the trap? Then we have to take into account this last term. Now in our trap, it so happens that the ion trap is much larger than the atom trap. So essentially in the region where there are atoms, the ion density is essentially constant, so you can pull it out of the integral, and what you are left with is essentially the number of atoms. So again, you can put it in a form of gamma IA times Na, and the solution of this is again easy to write. And again, doing some algebra, you can show that gamma IA, which is the ion atom collision rate, is related to the splittings you measure and to the photoionization rates, which we have already measured, and gamma B, which we also have measured. So okay, so we can find the collision rates, and so we can do a little bit more. So we know from theory that this gamma IA is related to the the cross section, the velocity, and the density of ions. And from theory, we know what the value of sigma v is, which is about this 10 to the power minus 14, 8 10 to the power 14. And so if we plug, so now if we use this expression, we can find out what the local density of the ions Ni is. It's just gamma Ia by Kia. So here's the plot. So this is the experimental result. So these blue squares show you how the photoionization rate changes with blue laser power, and the dots show you how the ion atom collision rate increases with power. Both are increasing because we are creating more and more ions as we increase the blue laser power. And the bottom graph shows you how the density of the ions is changing as we increase the blue laser power. We can go a step further because we know the size of the atom trap. We can tell what, and the ion density is essentially constant. We can tell how many ions are overlapped with the MOT at any instant of time in steady state, which is plotted in the on the right axis. So this is interesting and very useful because this is a non-destructive detection of the ion density, which is very difficult to do for ions that do not interact with light. And not only that, this is quantum state specific for the atoms. It measures the collision rate, for example, only for atoms in the f equal to 2 state. This can be extended to other ions or even to measure the interaction between atoms and atoms. Okay, so one could ask why do we use a low finesse cavity as opposed to a high finesse cavity? And the point is that if we use a high finesse cavity, then because the finesse is very high, the photon takes much longer to come out of the cavity, so the detection is much slower. So instead, if we use a low finesse cavity but a lot of atoms, then we can essentially do the experiments much faster, and within about 100 nanoseconds we can finish a measurement. It's a very rapid measurement also. So okay, with that, thank you.